All right, guys. Wrapping up our physics course. It's a brief little lecture, but it's got some complex graphs in it, both the tube rating chart and the anode cooling chart. And then, of course, I'm gonna talk about falling load generators. I don't think they're part of the credentialing content outline anymore, but you never know. They might throw in a question about falling load generators, so I thought I'd cover it just to be sure, because they don't go into a lot of depth and detail about what they just talk about generators. They don't specifically say falling load generators. I think they're just talking about the difference between three-phase 6 volts and high frequency and full wave rectified, but they might throw in a question about falling load generators, so you might need to know about falling load generators. So I'm going to tell you about that, in addition to covering heat units, tube damage, and these two different types of charts that we're going to look at. Okay, so for the credentialing exam, you have to do it the way that the techs back in the 70s and 80s did it, which is be able to look at a chart, whether it's a tube rating chart. And the point of a tube rating chart is to determine whether a particular exposure is going to exceed the maximum heat capacity for a tube. And then you have to interpret an anode cooling chart the way they did it back in the 70s and 80s. And that would be to determine how much time you have to wait before it's safe to make another exposure. Now, in the modern era, both of these charts are basically programmed into the software. So the computer that governs your X-ray tube and allows you to operate it will lock you out if you are about to dial up a technique that exceeds maximum tube capacity, or if you are not allowing for enough cooling time between exposures. It will lock you out if your heat capacity is detected to be high. It'll just give you a countdown timer on a little pop-up window, and you won't be able to take an exposure until the countdown expires, giving the anode enough time to cool off. So it's more of an automatic process in the modern era. You won't be using this on it, but it's important for you to understand what that software is doing and why it's doing it, because you don't want to blow up your X-ray tube. You really don't want to fry the components. And there's three components that are sensitive to heat damage: the anode, the glass housing, and the filament. Although the filament is usually governed, maximum filament amperage is governed before you even get to a chance to melt the filament. So it's very rare to melt a filament on a modern X-ray tube. You totally could do it back in the day, but um, with modern software controls and the safety lockouts, it's very hard to damage a tube in any of these ways. Most commonly, tube arcing, and no software controls can prevent an arcing event. And then just tube life. Eventually, the anode does wear out and gets like a mottled, cracked appearance to it. So not pitted like this, but like more like stippled in the focal track. So, and that eventually affects your focal spot size and your production of off-focus radiation if you don't have a smooth surface for your target anode. So, right. So, yeah, and so we're going to talk about those two charts. I think we start with the tube rating chart, and then I drop in what I know about falling load generators, and then we proceed to the anode cooling chart. There's not really representation of a housing cooling curve, um, but it's similar to an anode cooling chart. Okay. Um, the whole point is let's extend tube life. Let's not wear out our X-ray tube prematurely by abusing it, by stacking too much heat on it. Okay. All right. This is supposed to advance. Yeah, there we go. All right. So, heat units, effectively joules. A physicist would look at that formula and say, oh, that's joules. All right. So, why do we call them heat units? Well, I don't know. We keep making up terms, fancy terms, just because we have to be fancy and we have to have our own lingo, I guess. But heat units is totally joules. If you solve the equation kVp times Ma times time, well, that is, remember, voltage is coulombs or joules per coulomb, and then amperage is coulombs per second, and then you're multiplying by seconds. And so joules per coulomb times coulombs per second is joules per second. And then joules per seconds times seconds is just joules. See how that works? So heat units is joules. That took me like 30 seconds. Okay. And then there's this pesky little efficiency modifier. Okay. Well, we've made it much simpler than I learned it about the efficiency modifier. Okay. So the efficiency modifier is basically a function of your generator efficiency and related to the voltage ripple. It's actually related to the root mean square of the voltage. Okay. You don't have to know that. You just have to remember 1.4. Okay. I had to memorize 3 different efficiency modifiers, but you guys only have to remember 1.4. Okay. So the 3 that I had to learn was 3-phase 6 pulse is actually 1.35. 3-phase 12 pulse is 1.41, and then high frequency is 1.45. And these are all root mean square voltages versus full wave rectified voltage. Okay. But if you take 1.35, 1.41, and 1.45 and you put them on a number line and then you go to the other side of a long hallway and you kind of squint, those dots are really close together around 1.4. Okay. And so that's where we get the 1.4 for everything over 3-phase 6 pulse. So your 3-phase 6, your 3-phase 12, and your high frequency 1.4. It's basically estimation. It's rounding off to the average of those 3 numbers that I just mentioned. So just stick in 1.4 into your heat units formula, okay? Unless they specifically say full wave rectified. So if it's 3-phase 6, 3-phase 12, or high frequency, 1.4. If it's full wave rectified, or I doubt they would ask you about a half wave machine, or half wave rectified, the efficiency modifier is just 1. Okay? So 1.4 for our modern X-ray equipment. All right? And so this is how much heat in joules that you're going to, for any, you just plug in the technique. Those are the parameters for technique: kVp, exposure time, Ma station, and then efficiency modifier for your generator. And that gives you the joules output that's deposited on the anode. And yeah, technically it's 99%, but again, we're estimating. So yeah, we just lean back and squint. 99% kind of looks like 100%. So if you want it to be really technical, if you were dealing with an engineer, let's say, you would have to use the 3 different numbers for the 3 different power sources, and you would have to multiply the whole thing by 0.99. Okay, but close enough. Okay. So anyway, so we calculate for a given exposure, we can calculate the heat units like this. Okay, good. Well, there's a maximum heat capacity in heat units for any given X-ray tube. You can only load up so many joules before the tungsten anode starts cracking or pitting or warping or melting or whatever. Okay. So eventually, if you pour enough heat into metal, it will turn into liquid phase. That's bad. We don't want that to happen to our anode. All right. So that's where our tube rating chart comes in. And this is the example given in the Carlton Adler Balloch book, okay, in chapter 5. All right. So a tube rating chart is as shown here, and you can see that the x-axis is the time scale. Looks kind of funny, but it is a time scale. The y-axis looks straightforward or linear, and that's what's funny about the x-axis. It's non-linear. And that's kilovoltage for the y-axis. And then what I'd call the threshold curves or the threshold lines, those are the lines in red. Those are reflective of the MA station you select. Okay. Now, a tube rating chart looks very, very different than an anode cooling curve. And now the anode cooling curve and the housing cooling curve will look the same. And that's because they're both entropy curves. They're both heat loss curves. Okay. So if you have a system like the inside of an X-ray tube and you have a hot object like an anode, entropy says that that system will tend toward disorder. So at the beginning, the anode is hot, and you can sort it into the hot category, so to speak. But as time progresses, entropy says your ability to sort the system into hot and cold objects has to reduce. And so what that means is the anode has to give off its heat to its environment. And this isn't special to the anode. Every hot object behaves like this. It eventually gives away its heat until it approaches the same heat as its surroundings. Okay? The hotter it is, the faster it cools down. As it starts approaching ambient temperature, room temperature, the cooling slows significantly. Okay, we'll get to that in a minute, but that's basically how an entropy curve works. Okay, let's start though with the tube rating chart. All right, so the red MA lines on this chart are the safety thresholds. Your combination of KVP and exposure time has to come in below the safety threshold in order for it to be a safe exposure and not overload the heat capacity of the tube. Okay? So, for example, 100 kV at 0.2 seconds for a 150 MA station is perfectly safe. But 100 kV at 0.2 seconds for 200 MA stations is not safe. And so trace that out and see if you can tell the difference. And the difference is in the first case, the intersection point is below the red line marked 150. But in the second case, that intersection point is above the red line for 200 MA. So basically that's telling you can't set 200 MA 100 kV in 0.2 seconds. You're gonna damage your tube. But you can set 100 kV 0.2 seconds exposure time and 150 MA, and you won't damage your tube. Okay. So that's basically the secret to reading a tube rating chart is intersections below the threshold curve, the red lines, are safe exposures. Intersections on or above the red lines are not safe exposures. Okay? The farther you are above the red line, the more likely you're going to do heat damage to that tube. Okay. So this is a different author, and he's kind of messed with the tube rating chart a little bit. He swapped the position of the KVP versus the MA. He's got his thresholds. This is Bouchon. He has his threshold lines written as KVP limits, not MA limits, and then he has his y-axis as the MA. But the idea works the same. You got to find a point underneath the curves for the KVP setting that you're using. Okay. So if you're using 120 kV, you would pay attention to the dark green line. If you're using 150 kV, you would pay attention to the red line. And then the pink line, I think, is that's 70 kVp. Okay. But I'm showing you this because tube rating charts are written differently depending upon the author, and then therefore you might see a different tube rating chart than either of these two. Okay. But what I've drawn in here is how a falling load generator runs. So a falling load generator is going to basically try to maximize the efficiency of the heat capacity of the tube to stack on as much heat as we can in order to shorten the exposure time as much as possible. Okay. And so what happens is you wire for a falling load generator, you have to wire your tube for an auto rheostat, and it starts out at the highest MA station possible. And then as it approaches the safety threshold, that purple line, it's going to drop the MA station down to the next available MA station. So literally you're running, what is that magenta line? 80 kV. You're running 200 MA for the first 2/100ths of a second. And then the rheostat is dropping the tube current. The MA selector is dropping the tube current down to 150 MA and then running it at 150 MA all the way out to 1 second. And then, of course, we're meeting the safety threshold again. See how we're almost intersecting that purple line there? Okay. So then we drop it out to 100 MA and then we complete the exposure. We deliver the appropriate quantity of mass. Okay. I think if you multiply those up, I think it was like 100. It was either like 145 mass or 198 mass, something like that. But that's the shortest exposure time possible on this unit. Okay. If you tried to operate with a fixed MA, you'd be stuck with 100 MA, and you'd have to run it for over 2 seconds to get the same amount of mass. So we're able to cut the exposure time by over almost a quarter of a second, maybe even a half a second by running with a falling load generator. Okay. So it's just it's a special function. It's a special type of X-ray machine. You can spot a falling load generator in the wild because the exposure bell, the ringing sound that you hear during the exposure, it's actually going to sound like a... Give me just a second. Okay. So yeah, the exposure bell will sound like a bomb dropping. It will literally change the pitch through the exposure. So it'll, rather than a pitch of a constant tone, it'll more sound like woo, where the pitch drops through the exposure. That's reflective of the tube current dropping through the exposure because the bell is tied to the X-ray circuit. So as the tube current drops, the current through the bell drops, and you end up with a bell that lowers in pitch through the exposure. Okay, it's a dead giveaway for a falling load generator. Okay, Now, are they going to ask you about that stuff on the registry? Your guess is as good as mine. It's not specifically mentioned on the content outline. So I taught it to you just in case. Okay. Um, so moving on, anode cooling curves. This is an entropy curve. It's nonlinear. Mathematician would describe this as an inverse quadratic equation. Okay. So it kind of looks like y equals 1 over y, x equals 1 over, or I'm sorry, y equals 1 over x squared is the way that you get this graph. God bless. I had a little math seizure there. Good gravy. Okay. So why do I say it's an entropy curve? Because literally, specifically metals, because our anode is a big metal wheel, so it's a chunk of metal. If you were to conduct a science experiment where you had like one of those fancy, you can probably do it with if you get an infrared thermometer where you scan the temple, get yourself a nice chunk of iron and throw it in the bonfire, right? And then pick it out with tongs once it's safe, and then just rest it on a stone or whatever, right? And then just take its temperature over time and plot that in minutes on the x-axis and overall temperature of your big chunk of metal that's been heated up on the y-axis, and you're going to find that it traces this same curve. This is just what heat loss over time for a metallic object looks like. Okay, so it's not special to the anode, even though we call it the anode cooling curve, right? This is just a hot object cooling off. All right, sorry, was interrupted. Always happens. So it's rapid at first and it gradually slows. Well, when there's a great difference between the heat possessed by a hot object and its surrounding environment, it's going to shed that heat more rapidly. But as it gets closer and closer to the room temperature, the ambient temperature of the environment, then the rate of heat loss slows down significantly. Right? And this always happens. This is, and again, a physicist would look at this and say, oh yeah, that's a hot object cooling off. If you took away all the labels, maybe tell them that the y-axis is heat and the x-axis is time, they'll look at that and it's like, oh, you have a hot object and it's cooling off, and this is the cooling curve for that object. Okay, so it's not specific behavior to our anode wheel. Okay, this is just the graph you get of a hot object cooling off. Okay, and again, the anode cooling chart is integrated into the software controls. The computer operating system for our modern X-ray units is going to give you a pop-up window exposure lockout with countdown timer. Okay, but for the registry, you will have to know how to navigate this chart. And so I think I've got an example coming up on the next slide. Let's go to that. Yes. So a couple of facts here. The y-intercept you see on this one is 350 and then times 1,000, so 350,000. The y-intercept is always the maximum heat capacity of the tube, okay, for every anode cooling curve. So they might ask you that. They might ask you, what's the maximum heat capacity? It's always the y-intercept. So where the red line intersects the y-axis, the y-intercept, that number is always the maximum heat capacity. Okay, the maximum cooling time is always the x-intercept. That's 16 minutes. Okay, so those two facts first. Those are easy questions if you know how to look for the answers. Okay, so if they if they say what's the maximum cooling time for the X-ray tube that has this anode cooling chart, okay, and you would just look on the x-axis and see where the curve intersects the x-axis, and that looks like I would either call it 15 minutes or 16 minutes. I can't see it that well with my old eyeballs. Okay. But then they're also going to ask you a problem like the one I have posed here. So if an exposure is made that consumes 250,000 heat units or joules, how long do you have to wait before you can repeat the exposure? That is another 250,000 heat units. Well, the maximum heat capacity minus the exposure is the remainder of heat capacity that you have left on the tube. Okay? So, the maximum heat capacity is 350,000. Minus 250,000, 250,000 leaves you 100,000. Okay? So the tube has to cool from 250,000 down to below 100,000. So let's look at that on the curve. Let's find 250,000, and if we go over, you're going to find that that intersects the red line at a time t equals about 1.2, 1.25 minutes. Okay? And then go to 100,000 and look that up and go over to the line, and you're going to see that the red line is definitely below 100,000 at time t equals 4 minutes. Okay? And so you take 4 minutes and subtract 1.25 minutes, and that gives you your total cooling time necessary to make another exposure of 250,000. Okay? So if you load it up with 250,000 and then you let it cool for 2 3/4 minutes, then it will be at the 4-minute mark and it will be below 100,000 heat units. And so then it's safe to load another 250,000 because you'll still be under the maximum of 350,000. See how I did that? Okay. So you have to know where your start point is. That would be y equals 250, and then extrapolate that down to the x-axis to get your starting, basically your starting cooling time, and then what your target is under 100,000, and that would give you your ending cooling time, and then you take the difference of those cooling times, and that's the amount of time you need to move that many units on the entropy curve, that many heat units. So to descend from 250 down to below 100,000 takes about 2 3/4 minutes. 2 minutes 45 seconds. Okay? And that's typically how those problems go. Okay? The other version of this would be if they're not asking you what maximum capacity is or maximum cooling time is, they'll say that you have this first exposure that delivers this many heat units. Which of the following choices can you expose immediately? And it'll give you 3 different techniques, and you'll have to calculate the heat units for those 3 different techniques using the heat units formula, and then figure out which one you have capacity for still. Okay? In this case, it would be a technique that resulted in less than 100,000 joules or 100,000 heat units. All right, so there it is. Oh, I call it the rectification constant. Here, I guess that's what they do in the book. Okay. So for single phase, again, reiterating from slide, I think it's slide 2 or so. Single phase units have a rectification constant of 1.0. High frequency and 3-phase 6 pulse have about 1.4. Okay. Again, heat units are calculated by your software, your operating system for your X-ray machine. Okay. Um, your software locks you out if you dial up a technique that exceeds the tube capacity or the generator capacity, and it locks you out in the event of an anode cooling time accession. So if you have a single exposure, but then you're about to dial up another exposure that is going to exceed maximum heat capacity, it will ask for you to wait and let the tube cool off. And so it basically will iterate and it will enforce the anode cooling curve and prevent you from making an exposure too rapidly, allowing time for the anode to cool off. And then there is the proof that I gave you before that joules over coulombs, which is volts, times coulombs per second, which is amps, times seconds is just joules. Anode heat loading is a function of exposure factors, okay? And so heat capacity is dependent, maximum heat capacity is dependent upon the heat capacity primarily of the anode, the diameter of the disc, the revolutions per minute, and the focal spot size all impact the maximum calculated estimate of heat capacity for the tube. Okay. Target material can also greatly influence the anode heat capacity. The whole point of the graphite heel of the anode target wheel is for a heat sink to increase heat capacity of the tube. Okay. So how do you extend tube life and avoid damaging your tube? You're going to follow tube warm-up procedures. Some of the manufacturers have made this an automatic software process that locks you out from even starting an exam until you perform a warm-up procedure. I think that's very smart. Okay. One of the number one ways to damage an anode, you can crack an anode by heat shocking it. You might have noticed the phenomenon of heat shock if you've ever worked with cheap bakeware and you immediately put it into the sink after it's been in the oven. It goes from extremely hot to extremely cold really fast, and your bakeware shatters as soon as the cold water hits it. Okay. What's happening is you're putting the rapidly changing from cold to hot puts actual physical stress on the molecules that the object is made up of. And so you can create fractures in the molecular lattice, the crystal lattice of the material, whether it's a cheap baking dish or your anode. Okay. Avoid frequent and successive boosting. This is over rotoring. All right. Now in pediatrics, you got to time the breathing, so you're going to prep and rotor. Okay. But they do recommend in the modern era that you do not prep excessively. Okay. Now what's excessively? I would say for a period of longer than 5 or 10 seconds. Okay. If you are prepping and waiting for the patient to hold their breath and it's gone, you're prepping for a count of 5, the patient is not following your instructions. You need to get off the button, get back into the room, and tell your patient to follow the instructions. Okay. Use low MA settings. That's going to save you heat units. Use low speed rotor rotation. Okay. Follow the rating charts, which again is going to be controlled by the software. So if the software locks you out, don't try to override that by rebooting the computer. Avoid rough handling of the X-ray tube of itself, and listen for unusual sounds. Okay. Typically your unusual sounds that they're talking about is rotor bearing warp. So if the rotor bearings heat unevenly, They're supposed to be round spheroids, but they can become kind of ellipsoids if they get heated and cooled over and over again, or too fast or too slow or whatever. If they take on too much heat, the rotor bearings warp, and then you get this noisy anode rotation sound. Okay, it sounds kind of crackly. So that's because ellipsoids get stuck sometimes rather than rolling smoothly. Your warm-up procedure is to prevent that heat shock type thing and the shattering of the cracking or the shattering of the anode, because you went from ice cold to damn near molten in about 30 seconds. Okay. It also helps maintain the vacuum of the X-ray tube, because it prevents the tungsten from sublimating. Okay, so sublimation is when you skip the liquid phase and go right from solid to gas. Okay, and it can happen with most materials if you dump in too much heat too fast. Okay, warm-up procedures vary, but a typical warm-up procedure is medium energy exposures, 74 at 10 mass, and do that like 5 or 6 times. If it doesn't have a preset warm-up protocol, that's a sufficient warm-up protocol. Okay. If the tube has been resting or idle or not being used for an extended period of time, anytime, if you have a tube that's been dormant and not been used for exposures for greater than 2 hours, that's an idle tube and it's assumed room temperature. And so it's a cold anode. You should really warm it up before you start taking large technique exposures on that. The real trick is, if you want to crack an anode, do a cross-table lumbar spine on a hypersthenics patient on a cold anode. Load it up at 110 at about 600 mass and see what happens. Yeah, your anode's going to crack. Okay. Don't actually do that. Do the warm-up procedures, and then your tube will be slightly warm, and then you won't have that heat shock type damage effect happening. Okay. Tube failure, the most common cause of tube failure is tube arcing. Tube arcing will happen eventually. Okay. So that's how old X-ray tubes eventually die, is tube arcing. All right, so tube arcing happens when you vaporize the tungsten, and then that tungsten, after it loses heat energy, the vaporous tungsten precipitates back out as a solid dust on the inside of your glass envelope. Okay, if it gets to a certain thickness, it starts to develop principles of electrostatic induction in regards to the electron cloud that you're creating at the cathode. And so rather than the electrons heading to the anode, some of the electrons will short out on that thin coating of tungsten on the inside of the glass envelope, and that electric shock will deposit enough energy into the glass that it will crack the anode glass, and then you'll lose your vacuum. Okay. Once the vacuum is lost, your X-ray tube is gassy and it's basically non-functional as far as a modern X-ray machine goes. Filament breakage. Okay. So boost and hold, excessive rotoring, can cause damage to the rotor bearings, but more likely is going to cause your filament to overheat. Your filament, when your filament runs hot with preparation, boosting, your filament does glow red hot, which is just before it turns to a liquid as far as metals are concerned. Okay? And so the more you do that, the thinner the filament. The filament eventually thins out, and eventually it does basically evaporate away. Okay, you can evaporate your filament faster by abusing the preparation button and running excessive preparation. Now, again, in pediatric chest x-rays, you are going to have to prep and wait for the child to take in a big breath of air before you expose. So you are going to run preparation or boost a little bit longer before and hold that before exposure. Just know over time you are reducing the life of the x-ray tube. All right. Anode damage. Okay, so pitting is a single excessive exposure, and pitting used to be more common when there was no safeguards to make sure the rotor was up to speed. So back in the day, if you mashed all the way down and pressed both buttons, you would immediately started making x-rays on a cold anode that is not rotating as fast as it should be. And so you basically burn a hole, a melted hole into the anode focal tract like you see in the top picture. It doesn't happen as much anymore because um, the exposure switch won't activate until the rotor's up to speed. So there's always like a 1 second lag. If you mash down everything at once, there's always like a little bit of a lag, then the exposure starts. That's the rotor getting up to speed so you avoid pitting damage. Okay, so the software has basically fixed our ability to create pits in our x-ray tube. Now cracks, that's basically what happens to a sidewalk over time. So a sidewalk outside, uh, every night it gets colder, and then when the sun comes out during the day, it warms up. And then you repeat the process day and night, and then eventually your sidewalk has gone through hundreds of thousands of iterations of heating up and expanding, and then shrinking back down at night and contracting. And that over time produces physical stress in the concrete, and cracks develop. Well, the same thing happens with your tungsten focal tract. You heat it up, then you cool it down, then you heat it up, then you cool it down, then you heat it up, then you cool it down. It's exactly like what a sidewalk experiences. So why are we surprised that it cracks in old age? We're not. That's what it does. That's what everything does when it goes through a sinusoidal cycle, long term of heat and then cold and then heat and then cold. It eventually that creates physical stress on the material matrix itself, and cracks start to form in the material. Once you get nooks and crannies, like you see in the bottom picture, then you will increase the amount of off focus radius, because you will get x-rays made inside those channels and cracks. And then rather than a smooth surface, they're coming off of a pitted surface, and so you get more x-rays heading in a completely wrong direction than what you intended. So more off-focus radiation with a cracked old x-ray tube. Okay. And then warping, if the rotating anode heats unevenly, then the anode stem could warp, the anode wheel itself could warp, and the rotor bearings could warp. And all these lead to a wobbly anode, which completely ruins. It looks like there's motion on every image. No, it's your focal spot is jiggling up and down inside the x-ray tube because your anode is wobbling like a loose wheel on a shopping cart. Okay. So basically cracking the anode, you can still run that thing for a little while. If you've got a cracked anode, it will eventually arc out and just fry itself. But a warped anode, no, that thing's ruined. You got to replace that. Okay, and then also a pitted anode. You got to replace that too. All right, so that's the end of another lecture. We talked about the tube rating chart and the threshold lines. And remember, the rule is you got to stay under the line. The anode cooling curve, it's basically a subtraction problem with extra steps. Okay, and then I didn't show you an example of a housing cooling curve. They didn't have one in the text, but it's basically the same idea as an anode cooling curve. Okay, the difference is it's more critical, or um, it's more damaging if the anode overheats than if the housing overheats. Um, so the whole point of this, and to keep you mindful about heat units in general, is to understand that your X-ray tube is a machine. It's got moving parts and it's subject to heat stress, just like everything else on the planet. And so you can overload it and do damage to it. And the way that you do that is either setting techniques that are way too high, taking exposures too fast, and not allowing for adequate cooling time, or shooting on an ice cold anode, shooting a huge technique on an ice cold anode. Okay, over time, um, the X-ray tube does eventually wear out, and the number one cause of an X-ray tube failing at old age is tube arcing. Okay, second only to filament melting, or filament evaporation, as they call it. Okay. All right, that's it. We'll see. I think we got one lecture left to go in this series, and that's the conclusion of the physics class. So, see you for that next one.